Hello, and welcome. Today, we're going to explore a pivotal moment in the history of mathematics, the moment that challenged the very foundations of what was considered truth and reality. We're talking about the discovery of non-Euclidean geometry. For over 2,000 years, Euclidean geometry reigned supreme. Based on the work of the ancient Greek mathematician Euclid, it was considered the definitive description of space. Its axioms, like the famous parallel postulate, which states that through a point not on a given line, there is exactly one line parallel to the given one line, were seen as self-evident truths, undeniable facts about the universe. Generations of mathematicians tried, and failed, to prove the parallel postulate from the other axioms. They felt it should be provable, that it shouldn't have to be taken as a given. This seemingly minor detail would eventually lead to a revolution. In the 19th century, several mathematicians, Carl Friedrich Gauss, Nikolai Lobachevsky, and Janusz Bolyai independently began to explore what would happen if you rejected the parallel postulate. What if, instead of one parallel line, there were infinitely many parallel lines through a given point? Or what if there were no parallel lines at all? This led to the development of non-Euclidean geometries. Lobachevsky developed hyperbolic geometry, where the angles of a triangle always add up to less than 180 degrees. Bernhard Riemann developed elliptic geometry, often visualized on the surface of a sphere, where the angles of a triangle add up to more than 180 degrees, and where parallel lines always intersect. At first, these geometries were considered mathematical curiosities, perhaps even absurdities. How could space not be Euclidean? But the crucial point is that these non-Euclidean geometries were just as logically consistent as Euclidean geometry. They were built on different axioms, but they were internally valid. This was a huge deal. It shattered the idea of a single, absolute mathematical truth. It showed that there could be multiple, equally valid mathematical systems describing different kinds of space. This had profound implications, not just for mathematics, but for philosophy and our understanding of reality itself. If Euclidean geometry wasn't the only possible geometry, then perhaps our perception of the universe wasn't as fixed and objective as we thought. This opened the door to relativism, the idea that truth and knowledge are dependent on perspective and context. And it is no coincidence that later, Einstein's theory of relativity would use non-Euclidean geometry, specifically Riemannian geometry, to describe the curvature of spacetime. The universe, it turned out, wasn't quite as Euclidean as we had assumed. The discovery of non-Euclidean geometry also paved the way for postmodern critiques of objectivity. Postmodern thinkers, drawing on ideas from various fields, questioned the existence of universal, objective truths. They argued that knowledge is always situated, always shaped by power structures and cultural biases. The dethroning of Euclidean geometry, as the one true geometry, provided a powerful example of how even seemingly unshakable foundations could be challenged. So, non-Euclidean geometry wasn't just a mathematical breakthrough, it was a philosophical earthquake. It forced us to reconsider our assumptions about the nature of space, the nature of truth, and the very possibility of objective knowledge. It showed us that even in the seemingly rigid world of mathematics, there is room for multiple perspectives, for alternative realities. What do you think? Did the discovery of non-Euclidean geometry fundamentally change our understanding of reality? Or is it just a different set of tools for describing the same underlying truth? Let me know in the comments. And if you enjoyed this exploration of the philosophical implications of mathematical discoveries, be sure to like and subscribe. Thanks for watching,